I hope everyone is doing well. Welcome to the demo video of our software Vidyutik Urja Prabaha NiyantraSim. In this video, I am going to show one of the very interesting features of our software NiyantraSim. I shall show how inertial response from wind turbine can be simulated using control blocks in our software. At first, open the software, go directly in the canvas. To demonstrate this feature, we have already prepared a control system of reed thermal power plant. Here, the block comprises of governor, non-reed turbine, reed block, rotor under load, load change, droop, etc. By right-clicking on the block, we can change or set the parameters of each block. Now, we will see the frequency response of this thermal reed power plant. So, I have input the data. So here we can see the nadir is at 0.3614 Hz. Now I will connect with DFIG. Here I am taking 5 DFIG with 2 MW rated power. From left panel, just click on the DFIG block, connect with the system by right clicking on DFIG block. Start connection and end connection option is there. With the help of that, we can easily connect the DFIG block to the system. After that, we will put the parameters of DFIG. So here our connection is almost done. Now we will see the parameter of DFIG. Rho air density, R rotor radius, rated power of DFIG, rated wind speed, cut-in wind speed, cut-out wind speed, velocity of wind, penetration level, H inertial constant of DFIG, Ki inertial gain, Ri DFIG through gain, T lockup frequency filter for noise in the system, rate limit maximum rate of change of power, P limit upper limit on per unit active power, T limit upper limit on torque, omega minimum minimum allowable rotor speed, omega maximum allowable rotor speed, system base. The system base is the base on which we are working, like here on 20 megawatt base. CPU optimal power coefficient at design tip speed ratio, lambda optimal tip speed ratio. With these parameters, we can design EV turbine. So after that, we will see the result by adding the DFIG in the system. Here we will see DFIG speed versus time graph. So here we can see the nadir is improved now, but very less. Oh, I have taken 100 megawatt system base. So taking 20 megawatt system base, we will see the impact of DFIG. Now we can see nadir is improved up to 0.3148 Hz. The lower graph show rotor speed characteristics. If rotor speed is above rated pitch control, hold it nearly constant. If it below the rated, the turbine following the MPPT curve speeding up towards the optimal or slow down when giving the frequency support. Now we will see the inertial response graph. It is the immediate release of stored kinetic energy from rotor to oppose a sudden drop in a system frequency. So here, inertial response of DFIG at different wind speed. The wind speed lower than the rated speed give power from rotor kinetic energy, and after some time when system is stabilizing, it take power from the grid and obey the law of conservation of energy. And when wind speed is greater than the rated speed, pitch control is applied. When load increases, it places turbine perpendicular and take power from the wind, and after that it settles down at initial value. It is not using the deceleration of rotor speed. Now we will see the contribution of power from DFIG and reheat thermal power plant. So here DFIG produced initially 8.5 megawatt. As load increases, it gives inertial response to stabilize the frequency response, and thermal reheat plant produced 11.5 megawatt. This is the DFIG aerodynamic curve. It is also known as the MPPT curve, the mechanical power versus rotor speed curve. So, how much power a wind turbine can extract at different rotor speed. In region 2, power rises steeply following the MPPT trajectory because increasing rotor speed allows the turbine to maintain the optimal tip speed ratio for maximum efficiency. Once the rated speed reach, we enter in region 3 where pitch control actively limit power to rated value to protect the turbine. For different wind speed, each aerodynamic Pm versus omega curve shift upward because higher wind provide more available power. The MPPT optimal path connects the peak efficiency operating point of all these curves at every wind speed. The turbine adjusts rotor speed to stay on the optimal tip speed ratio, ensuring maximum power extraction. So, we firmly believe that our Swadeshi software will be a competitive alternative to the available costly foreign software in this domain. It will help not only the power industry, academia, but also organizations in their study and research. Thank you.